Dear committee, dear guests, I'm pleased to introduce Anna Németh, whose academic and clinical career has been closely tied to Semmelweis University. Anna was born in Zinc and grew up in Bakony-Szentkirályi with her parents and two older brothers. She attended primary school in her village and later graduated from secondary grammar school in Győr in 2015. Anna began her journey in dentistry at the Faculty of Dentistry of Semmelweis University, where she completed her dental degree summa cum laude in 2020. As a student, Anna actively participated in undergraduate research through the Scientific Students Association. She carried out her TDK work at the Department of Prosthodontics within the Digital Dentistry Working Group, focusing on intraoral scanning and 3D printing technologies. Her project, titled Comparative Evaluation of the Accuracy of 3D Printed Dental Models, earned her third prize at the university's TDK conference. Since September 2020, Anna has worked as a clinical dentist at the Department of Prosthodontics at Semmelweis University. In 2023, Anna successfully completed her specialist training and received her board certification in prosthodontics. Since 2024, she began working as an assistant lecturer at the university. She is involved in patient care, teaching dental students in both Hungarian and English, and she is a clinical instructor and lecturer, and she actively participates in organizing courses and serves as an instructor in the field of digital dentistry. As part of the basic restorative digital dentistry elective course, she teaches 3D printing to undergraduate students. She delivers the 3D printing module to doctoral residents during the postgraduate digital dentistry education week. She teaches 3D printing in the Digital Dental Designer postgraduate program. In addition, she served as an instructor on intraoral scanning courses and has been actively involved for several years in our department's validation study of intraoral scanners. She started her doctoral studies at the Doctoral College of Dental Research at Semmelweis University in 2020. Her research focuses on digital dentistry, particularly the application of 3D printing in prosthodontics. She has participated in several international and national conferences. She presented her work at the Semmelweis Symposium in both 2022 and 2023 in Budapest, at the IADR Oral Health Research Congress in Geneva in 2024, at the DDS Global Congress in Casablanca in 2023, where she won the second Best Poster Prize. In her free time, she enjoys folk dancing, reading, and spending time with her friends and family.
Dear professors, dear committee, dear audience, let me introduce you my PhD topic, which is 3D printing in dentistry. I'm Anna Németh from Department of Prosthodontics, Semmelweis University, and I have always been interested in digital dentistry, especially in 3D printing. So my vision is to enhance patient care by integrating high-quality digital prosthodontic treatment using 3D printing as a daily routine. And to reach that, I would like to adapt 3D printing to clinical practice and to bridge the gap between the advanced and everyday dental care. My specific goal is to evaluate the accuracy of 3D printing technology by investigating dental models and fixed dental restorations. My first project is a clear guidance to select the most accurate technologies for 3D printing dental models. The biggest breakthrough in modern-day dentistry was the advent of CAD/CAM technology because it provides precise restorations and time-saving manufacturing. It comprises additive manufacturing, as known as 3D printing or rapid prototyping, where the three-dimensional object is built up layer by layer based on a virtual model. The importance of this topic is shown by the increasing number of the publications. There are several 3D printers with different technologies, but the problem is that the result about the accuracy of this technology in the literature is inconsistent. And even in the digital world these days, there are some cases when we need tangible physical casts during our prosthodontic treatment with mechanical articulators to evaluate the occlusion, articulation, to execute veneering, or to adjust the approximal contacts. So there is a need for more evidence about the accuracy of this technology to replace the conventional methods. Therefore, we aimed to investigate the accuracy of 3D printed dental models fabricated with different technologies, and we evaluated our results in terms of clinical acceptability for prosthodontic and orthodontic applications. We conducted our work based on the PICO principle, and our question was, do dental models manufactured with different fabrication techniques provide the same accuracy compared to the initial digital model? And our hypothesis was that the accuracy of these models are within the clinically accepted threshold, regardless of the printer type. And we defined two limits, 120 micrometers for prosthodontic applications and 250 micrometers for orthodontic applications. I made my systematic search on 4 databases based on a defined search key. And after the long selection process, I ended up with 11 eligible articles for the analysis. Because of the heterogeneity of the included studies, a subgroup analysis was needed. And we made that according to those factors which have the greatest effect on the printing accuracy. These are layer thickness, model design, the measuring level, and the calculating method. The first one is the layer thickness, because it largely affects the surface quality of a 3-dimensional object. We can see the difference running the printing on 100 micrometers or on 16. The second one is the model design. Based on a study, these horseshoe-shaped models are significantly less accurate than those models which have a horizontal connection bar, so we needed to evaluate them separately. Third one is measuring level. We can measure the accuracy on full arch or on smaller segments. And based on the calculating methods, we differentiated 2 calculation metrics, whether the results were expressed in root mean square or in absolute mean deviation. Based on these, we had 6 subgroups. Based on our included extracted data, we were able to make a network meta-analysis where we can compare the interventions to the control and the different interventions to each other as well. So we can combine both direct and indirect evidence across the network of studies. These network diagrams shows the composition of the network of each subgroup, where the nodes representing the different technologies and the lines between them, the available direct comparison. Then the leak heat plot shows the mean difference for all possible treatment pairs, and the forest plot shows the mean difference of each intervention compared to the control group, expressed in micrometers. In this subgroup, we evaluated the trueness, expressed in root mean square, measured at arch level with a layer thickness of 50 or less. We can see that all investigated technologies were within the orthodontic clinical limit. However, from the prosthodontic aspect, only PolyJet, DLP, and SLA technologies were clinically suitable. Here, in another subgroup, the measuring level was tooth level. Based on our results, we can see that tooth level measurement lead to better accuracy results compared to arch level measurements when the other parameters are the same. In this case, we can say that during smaller section accuracy analysis, a section-based alignment is made in the software, which significantly improves the alignment accuracy. That's why the distortion is much moderate. So in this case, all evaluated technologies were within the prosthodontic limit. And these results support the fact that applying a smaller layer thickness lead to better surface quality and better accuracy results, because in this case, PolyJet and PolyJet technologies provided the best results, and they used 16 and 30 micrometer layer thickness. Based on our results, we can conclude that SLA, DLP, and PolyJet technologies are clinically acceptable for full arch dental model production. The filament techniques, LCD, and clip technologies are not suitable for prosthodontic applications, and the layer thickness for 50 or less is considered to be optimal. The strength of this work were that it was the first meta-analysis in this topic, and since it was a network meta, we could combine both direct and indirect evidence, so the evidence of the practical applicability was much higher. However, we could only evaluate the horseshoe-shaped models, and we had some incomplete data in the studies about the printing parameters. From the practical side, we suggest the use of SLA, DLP, and PolyJet technologies for full arch production. But from the research perspective, we assume that a standardized accuracy assessment protocol is necessary to facilitate comparisons, and future studies should also involve a standardized reporting protocols about the detailed printing parameters. My second project is a comparison of fit and trueness of single unit and short span fixed dental restorations fabricated by additive and subtractive manufacturing. CAD can be divided into subtractive and additive manufacturing. We use subtractive, as known as milling, for over 40 years now, but 3D printing is a younger technology. But we expect the same precise result from both of them. However, there are many differences between the two fabrication methods. The main difference is the material wastage. In case of milling, rotary instruments remove the material from a solid block to create the desired shape, and the trimmed material is a waste. However, during 3D printing, the residual material can be reused again, and the waste is less. Complex parts with intricate shapes and hollow cavities can easily be produced with 3D printing, but in case of milling, there are some limited capabilities because of the sizes and the angles of the milling burrs. The internal fit and marginal fit in case of indirect restorations are critical factors for the restoration's long-term success and long-term durability. And numerous studies have already been published evaluating the 3D printed restorations adaptations, but again, the results are inconsistent. So we aimed to compare the fit and trueness of additive manufacturing to subtractive manufacturing on fixed dental restorations. We evaluated fixed partial dentures made by 3D printing compared to milling, and the outcomes were marginal fit, internal fit, and trueness. And we hypothesized that fixed restoration using by 3D printing are significantly more accurate than those made by milling. I made my systematic search on the big databases, and at the end of the selection, I had 57 eligible articles. The following parameters were analyzed. We evaluated internal gap, which is the perpendicular measurement between the inner surface of the restoration and the prepared surface, and we measured it on the axial and occlusal surfaces. Then the marginal gap, which is the perpendicular measurement between the margin of the restoration and the preparation margin, and the absolute marginal discrepancy, which is the angular combination of the marginal gap and the extension error. We evaluated also the trueness, focusing mainly on the marginal area, and we differentiated the results based on the material, so we evaluated metal, acrylic resin, and ceramic restorations. Now, these forest plots demonstrate our results. The vertical line is the null effect line, and the horizontal axis shows the mean difference between the fit of the additive and subtractive restorations. If the point estimates of the individual studies are placed on the right side of the null effect line, it means that the gap was higher in case of subtractive restorations, but if it's on the left side, it means that 3D printed restorations showed higher gaps. The diamonds at the bottom of each subgroup show the overall effect of the interventions, and if they are in contact with the null effect line, it means that there were no statistically significant difference. So based on that, at the first measurement, the internal fit on the axial surfaces, we observed no statistically significant difference between the two manufacturing methods in either of the subgroups. However, measuring occlusal internal fit, milled acrylic resin restorations showed a significantly higher gap compared to the 3D printed ones. It maybe can be explained by the phenomenon of drill compensation of the milling machines, which occurred due to the softness of the acrylic resin material. When measuring marginal fit, we observed no statistically significant difference in either of the subgroups between the two manufacturing technologies. But in case of marginal trueness, we saw that 3D printed ceramic restorations showed a reduced marginal trueness compared to the milled restorations. In this case, the explanation is that the composition of the ceramic suspension is critical in the printing process because it requires high solid loading, homogeneous dispersion, and low viscosity. So we can see that the properties can be conflicting, that if we improve one of the factors, may it negatively affect the other factor. So that's why developers face a lot of challenging in case of printable ceramics. Based on these results, we can say that additively manufactured fixed restorations are a valid alternative in the digital workflow. There were no significant difference in the adaptation between the 3D printed and milled metal and ceramic restorations, but 3D printed acrylic resin restorations showed a better occlusal fit compared to the milled ones. However, the 3D printed ceramic restorations showed a reduced marginal trueness compared to the milled restorations. We could include a large number of publications into this study, mainly from the last 5 years. However, we know that the scope of this work was huge, so we had some heterogeneity in the testing protocols and the printing techniques as well. But we support the use of additive manufacturing for indirect restorations. However, more in vivo studies are needed in the literature, which made based on a standardized assessment protocol. And we think that it's time to reevaluate that 120 micron clinical acceptability threshold, because we already have newer restorative materials, newer luting cements, and the measurement techniques are more modern and more precise, which are available now. Here you can see my scientometric data and my publications related and not related to the thesis. Besides my PhD work, I work in the education of Hungarian and English language dentistry and digital dental designer students as a clinical instructor and lecturer. And I also participate in special trainings for postgraduate students. And I'm a member of the Digital Dental Working Group, where we evaluate different printers and intraoral scanners. And I also attend in international conferences where I present my work in form of posters. I am deeply grateful for the many people who helped me during this journey, especially to my mentor and supervisor, Judith Borbély. Her expertise and hard work was always really inspiring me. Thank you for Professor Peter Hermann and the Home Institute for the support during this journey. And I would like to thank Professor Péter Hegyi and Professor Gábor Varga for their support during the program. Also, Viki Vitai, my co-investigator, and Bence Szabó, the special person, the statistician, and to all my co-authors and collaborators. And I am deeply grateful for my friends and family, and especially my partner. And I would like to dedicate this work to my mother, because her unwavering love and belief in me was always my driving force. And I would like to finish this presentation with this quote: just remember, you can climb the ladder of success with your hands in your pockets. Thank you very much.
Thank you for your nice presentation. I expected some additional activities like hobby, sports, or whatever. You should have something like that.
After the PhD finished.
Of course. So I would like to ask the opponents to shortly read the... Are you going to read the to review? Or is it not official? We shouldn't. Okay, so just the question. Okay. So then please, okay. Because we have like that in normal, in regular form. Okay, thank you.
Thank you. All right, I'm one of the opponents. So Anna, we already met, I think, before, maybe in Casablanca. Yes. Thank you so much for a very clear presentation of the two research works. I've written down some things, but we are with different jury members, so I will pick out some of my ideas which I want to discuss with you, and then I present to the others for additional questions. The first thing I want to discuss is when you selected these studies for inclusion in your first and your second study. I was triggered by the fact if you go to printing accuracy or precision or trueness and all those metrics who determine if you can use it in the clinic or not. Actually, the input data, was this always like an intraoral scan, or was this also a CBCT scan? Were there different intraoral scans? Did you look into that?
Yes, thank you for your question. In case of the first study, where we evaluated the models, always the reference scanning was made by a desktop scanner, mainly from 3Shape and Medit desktop scanners. So these gave the virtual data for the...
From a gypsum model then, from an original?
There was a reference model, just an STL file, a digital file. They printed it with a specified printer with different technologies. Then they had the models, and in this case, the reference scanning method was made with a desktop scanner. So when the reference model was there at the beginning, and the rescanned models were compared in a software with superimposition and so on.
So you selected studies that did this. And then
Yes.
my question was, because you have, if you go to the literature of the printing, you have articles who compare digitally, and you have articles who compare the printed versions. But when you have 3 printed models next to each other, how do you compare them?
Yes, so the accuracy is given by trueness and precision. So if we would like to evaluate a printed model and we compare the back digitalized data with the original, it means the trueness, how close it to the original reference scan, which was just an STL file. But we can measure the precision, the repeatability of this printer. When we print that exact model for 10 times, then we can compare them to each other as well. This will give the repeatability of this model. So in these studies, always there were printed models, physical printed models, which were evaluated and measured back to the original data.
How? How? Because I didn't, yeah, how were they measured back to the original data?
So in a software, it was usually...
But that means that you digitalize them again.
Yes, yes.
But then you increase or you decrease the accuracy again, and you increase the error again,
yes,
you have
now
them.
I understand.
Yeah.
Yes.
Yeah.
Yes, it's a limitation of the first study that those desktop scanners they are described that the precision of them and the accuracy of them are 6-10 micrometers, but we eliminated that problem from that circle. So
yeah.
we thought that they are good tabletop scanners, and the back-scanned data, the reference-scanned data is the true data about the 3D printed model.
Yeah. Yeah, it's of course not your study. Yeah? It's critically evaluating other
yes,
studies.
Yes.
So coming then to the clinic, which is your field, there you use the printers. So how many of the printers that are actually out there when you go to Congress or when you look to the different digital practices in Hungary, how many of these printers are discussed in your articles?
Actually, in Hungary, it's not spread yet. Not at all, because I think that dentists are afraid to use it and to use them instead of the good old ceramics or instead of other things. But yeah, there are some systems which are quite popular, and some in the practices we can find them, but not much. And also those which were included in my studies, for example, the sprint tray system or the NextDent system, Formlabs, and so on. They are used in Hungary, but not that much yet, hopefully.
Yeah, and because you now name some commercial companies, of course, each of them has also a full set of printing materials, and you discuss like zirconium and other, but how much did you look into that? How much that may affect the accuracy and trueness? And because each printing material needs another design probably also. Yeah.
Yes, this is also a limitation of this second work, that we group the material based on the big group like the acrylic resins, the ceramics, the metals, but there are many differences, the composition of those, each resins. And especially in case of the printable ceramics, they are really risky to evaluate them. Maybe now they start to more developing, but yes, we need to evaluate them separately based on their conditions and compositions.
Okay, thank you, Anna. I have other questions, but I think we can.
We have a question.
In fact, I have a question a little bit in connection with your last answer. How you can evaluate on the same printer different materials?
In case of models or in case of restorations?
Everything for both for both studies, the same interest.
So in case of models, and thank you for the question, in case of models, we evaluate the digital models with the help of superimposition, where we can see the mean difference between the two models. But in case of restorations, when we would like to evaluate the fit, the internal gap and the marginal gap, and also the trueness of these restorations, there are quite a lot of methods. There are non-destructive and destructive methods for evaluate especially the fit. The most common technique and the most cheap technique is the silicone replica method, where we put some flowable silicone into the crown, then we put the abutment, and we evaluate that tiny space which filled by the silicone, and we can measure it in microscope. Or there are some direct methods, for example, micro-CT or optical coherence methods, where we can see the fit of these crowns, or we can see the trueness, like the three-dimensional fit of these restorations, where the so-called triple scan method is used, when we scan the inner surface of the restoration, the prepared abutment, and their assembly together. And now then after that, we can make the evaluation in the program.
Yes, but for example, we cannot change the accuracy of one printer only changing the material. For example, have a better result with maybe normally less better printer, only changing the materials?
Great question. Actually, the printers are divided into open and closed systems. A lot of systems like Sprint Tray, Formlabs, and these popular systems are closed, so only their own material can be used in these cases, and they are really great because they are developing these materials for that exact printer. But in case of the open system printers, we have a wide range of materials what we can use, and in this case there are interesting results that if one of the material is better than the other, what is the reason?
Thank you.
Thank you.
Thank you. Is there any more question from the committee?
Thank you for your presentation. What would you say that could be the future perspective? Is it milling or printing?
Great question, thank you. On the side of printing, I think it's definitely printing. And the main reason, I think, is the waste. In this case, is because there are big discs and blocks we use in the milling machines, and the wear of the milling burrs and so on. They are kind of expensive compared to a 3D printer, where we have a vat of resin material. It's enough for, I don't know, 2,000 crowns, and they are precise. And we just need to sometimes change those resin tanks, but I think there are a lot of opportunity in 3D printing. For definitive restorations, for example, this technology is not there yet because of the problems of the ceramic compositions. But for the other things, like guides, models, and so on, it's really great. One machine for everything, actually. So the future is in 3D printing.
Yeah. And I would like to add on that, because you need a somewhat less accuracy than she needs, because you are orthodontist and she's prosthetic dentist. So. But coming back to that accuracy, I think at the end you mentioned also the 120 micrometers, that it's time to revise. So I thought of a little question for you. Do you think you have to work, if you are dealing with crowns, you have to print on an implant bridge? Do you need the same accuracy as crowns on teeth? Is it exactly the same, or do you need more accuracy when you have implants or when you have teeth?
Thank you for the question.
Physiological question.
Yes, I think we need to be more precise in case of natural teeth. But of course, for the implant is also really important. But I think there is a wider range in case of implant prosthetics. But when we are thinking about the cement dissolution, the secondary caries, the inflammation on the gum, I think it's more important to be really precise and accurate there. And 120 micron is a lot.
I think it's too much for prosthetics.
Yes.
Yeah, because humans can feel much smaller errors. That's your most complicated patients, the patients that always call back, it's not accurate, I can't adapt. Yeah, but okay, thank you.
Thank you very much. Okay. Yeah, you have it.
Can you hear me?
Actually, I can hear you, thank you.
Okay.
Yeah, but maybe the audience.
But the audience, yes.
Okay. Now you
great.
hear me. So I was inspired by your Arnold Schwarzenegger quote. So I am curious about the strongness, the durability of that thing. So I know that the material is fixed. And of course, the durability depends on the material, but maybe it also depends whether it's mining or printing. So what do you know about the durability of the techniques? It is the same, doesn't influence the choice? This is my question. Thank you.
Thank you. Actually, for milling, we have already a wide range of materials already developed, and in the clinical world, it's been used for years now. And totally other factors come to the accuracy in case of printing, because I think for printing, more factors can affect the final result. One of them is the layer thickness, what we use. It's a great effect. What I already mentioned, those factors, and in case of milling, I don't think there are as many points where we can fail.
Okay, but so how long they work? So which time it's needed to change them in the mouse, basically?
Thank you for the question. We suggest these like definitive materials, for example, ceramic or zirconia restorations for 8 to 10 years, but if they are cleaned well and the oral hygiene is good, then they can last more. But we don't have enough data yet for the 3D printed restorations. So there are not a lot of in vivo and clinical studies for these 3D printed restorations, because we just have the materials what we can place into the mouse just a few years ago. So
there wasn't enough time to get the results.
Not yet.
But it was interesting to see the results later.
Thank you.
Okay, thank you very much. Very interesting presentation and huge work, because after initial search you have in one study 16,000 and in other study 4,000. And
yes.
I'm wondering, how did you manage to come from 16,000 to these few studies which were included? So I'm really wondering how you did it.
Thank you for the question. with the help of some co-investigators. So we divided these 16,000 articles to 8 and 8. So we searched through 8,000 and 8,000, and at the end only 11 was suitable. It was a surprise.
And why did not you consider to change searching strategy in this case? Because 16,000 means that it's something to...
Yeah, thank you. We tried to change it. Actually, in the search key, only the population, so the dental models words were there, and the intervention, which was the 3D printing. We tried that we put the comparator part and the outcome part into the search key, but much, much less articles were there, and we found some key articles which were excluded from that search compared to the 16,000 search. And we tried with many forms, but we accepted after a time that we need to do that 16,000.
It's a very good topic. So, until I have a question that in the first project you said you made a network analysis, just you had no time for showing it, just the control to the just compared to the control group. But you mentioned that the PolyJet resolution was only 60 micrometer, which I was surprised because I didn't know that there are better than 50 micrometers in the market. But do you see, or have you seen any differences based on these very high resolutions? So was them better, or?
Yes, actually, some years spent after this project was made, and on the today's articles we have much more data which show that the today printers are more accurate, and especially the PolyJet printers. And the brother of the PolyJet printer is the nanoparticle jetting technique, which they belong to the material jetting category. They show the best results, and this nanoparticle jetting technology is the best in case of the ceramic printing, because they can inkjet that tiny, tiny layer, which is 16, and in case of MPG is 10.5 micrometers, which is really small. And we don't, in these cases, we don't have that staircase effect. In case of 50 micron, not much, but on 100 micron, we can see with our eyes those stairs on the models. So yes, they are much greater. And one big advantage of this PolyJet technology that it's able to use different materials at one time. So great, great stuff. Maybe it can help to Dr. Koenig with the printing for the epitasis. PolyJet is the great way.
Not too many. So then if there is no more question.
Comment, congratulations for presenting quite well the non-trivial statistical topic of network analysis.
Thanks
for your presentation.
Thank you.
Okay, if there are no more questions, then I will close temporarily the discussion, and then we go to the private room to discuss the result. Okay, thank you very much.
Thank you so much.
So I officially open again the defense, and I would like to announce the results which were given by the committee members. It was a very hard talk and hard discussions. So altogether, the average mark is 4.8, and it is assigned to summa cum laude. Congratulate for your work. And I hope that you will succeed in the next project as well, and then you don't give up and don't finish the research and beside of the clinical work. Okay? Congratulations. And I'm closing the session.